Welcome back to the channel. In this video, I'll demonstrate something you haven't seen anywhere else: an information graph implemented with biologically modeled neurons. These demonstrations reveal how a network of simple simulated neurons can store and retrieve knowledge in a way that mirrors how our own brains might work. I'm Charles Simon, longtime AI researcher, software developer, and manager. Beyond AI, I've developed software for neurological test instruments and neural simulators. I created the Future AI Society to explore how neuroscience can inform smarter, more human-like AI. I'm using our open source simulations and demonstrations throughout this video series, and if you want to experiment on your own, you can download the BrainSimulator 2 from GitHub and try out these neural circuits and suggest improvements. We know from observing how we think that in our brains, knowledge is arranged in some sort of graph of relationships, as I've explained in other videos. The question is, how could a graph be implemented in neurons? To that end, I've built a small graph in my neuron simulator, and I'll show you what it does and how it works with 3 demonstrations. There's a link to download the BrainSimulator and the demonstration files in the description below so you can try it on your own. So let's dive right in. On the right side of the screen are cortical columns. Each is a vertical column of 15 neurons representing a tiny fraction of a neocortex. On the left is an input and output section built in horizontal clusters of 7 neurons each, which could conceivably represent activities of the thalamus. In between are 6 hard-coded relationship types and a bit of control circuitry, which could conceivably be in the hippocampus. Each circle you see represents an individual neuron, and the lines are synapses connecting them. The arrowheads indicate the direction of the connection, while the colors of the lines show the type and weight of each synapse. Some synapses even have little bar graphs that update to show their current weight. All the neurons and synapses you see are pre-allocated. The only things that change in these demos to represent information are the weights of selected synapses. We can think of this pre-allocated structure as akin to the brain's initial structure as governed by your DNA. Although the brain structure can change, this happens over time frames much slower than our immediate thinking processes. I can click on a neuron to force it to fire, and when a simulated neuron fires, it flashes white. Neural spikes leave a neuron and travel along axons as animated dots moving down the connection lines. Many of the neurons are configured to fire in bursts of spikes, just like real neurons often do. The columns and clusters were created as software modules within the BrainSimulator and will automatically set up all synaptic connections. You can think of these as the DNA of our simulated neocortex, and it means that we can easily extend the system to any number of columns and inputs. I've already given this network a bit of information about Fido and dogs, as you can see from the labels I put on the input-output section. So I'll start by showing how information can be retrieved. Let's try some examples. If I fire the Fido input neuron along with the ISA neuron, the system retrieves the information that Fido is a dog, and you can see the output neuron of the dog row firing. Similarly, I can ask the question, what is Spot? And find out that Spot is also a dog. I can ask for the attributes of Fido by firing the has a relationship and see that Fido has a collar. Retrieving the attributes of objects is one of the things that your brain does a lot of. I can even ask for instances of dogs, and the network will give me both Fido and Spot as the answer. So far, so good. But let's add a bit more by asking what is a dog, and we learn that a dog is an animal, and we can ask what is an animal, and an animal is a living thing. Now let's ask what is Fido while also enabling the recursion relationship type. You can see that Fido is not only a dog, but is also an animal and a living thing. And if you watch carefully, you can see that these facts fire in order as the search works its way up the hierarchy. We can take it further. If I ask for the attributes of a dog, I'll learn that dogs have fur and a tail. And here's where the system becomes even more powerful. I can ask for Fido's attributes recursively. So not only does Fido have a collar, but Fido has fur and a tail because he's a dog, and he can move because he's an animal, and he grows because he is a living thing. This illustrates the first step toward attribute inheritance, which is a huge concept for how your mind works. You don't need to remember all the attributes of anything. You only need to know what makes a thing unique. You don't need to know that Fido is subject to gravity because you know that Fido recursively is a physical thing and all physical things are subject to gravity. Your entire world of knowledge is hiding inside attribute inheritance. In this neural simulation, I have not implemented either firing just the attributes or handling exceptions, but I think I've provided enough groundwork that you can see that this is possible and how you might do it if you downloaded the Brain Simulator and tried. All of this is happening with simulated neurons, and it's fast. Most retrievals happen in just a few milliseconds, and extremely energy efficient. Even during recursive searches, only a tiny fraction of neurons are firing at any given time. My simulated cortical columns only have 15 neurons, while real ones have about 100, so it's easy to envision how many capabilities could be added. Like the suppression of extraneous search results, exceptions, or additional relationship types. Another important observation is that the labels don't matter. The neural array doesn't know anything about the meaning of the data. I've just put labels on a few neurons so it makes sense to us in the demo. But the network and the neocortex could just as easily store logical information, visual patterns, sounds, spatial information, or any other type of knowledge. And in future videos, I'll expand on this versatility. Now let's move on to how information got into this network. To start, I'll reset the content of the system. All learning synapse weights are cleared, but the synapses themselves remain. Then by firing inputs like Fido, the system detects that those inputs aren't connected to any cortical columns. It searches for a free column and uses it. Connections to and from the column are made automatically. So I'll start by adding all the inputs I'll be using in this demonstration. Now we'll add the knowledge Fido has a collar. To do that, I simply fire the Fido input, the has a relationship, and the collar star neuron. Neurons like collar star are desired outputs. The system strengthens the necessary synapses so that later when I ask about Fido's attributes, the collar out neuron will fire. All information is stored in the strengths of synapses in this area of neural columns. Adding Fido is a dog works similarly, but under the hood there's an extra feature. Because if you know that Fido is a dog, you also know that the set of dogs includes Fido. This is handled with the inverse relationship, dog has instance Fido. This can be created automatically with a little circuitry which swaps the inputs and outputs and enables the inverse of the relationship type. I'll show details in a moment. How does the system know if you're searching for existing information or adding new information? Simple. If you give it a source and a relationship type, you're looking for information. If you also define a desired output, then you are directing the system to learn a new fact. I've shown the has a relationship type, but not its inverse. The inverse is the part of relationship, and the part of relationship is how your brain searches for content. That is, you can ask what has a collar and a tail. Your brain does this all the time. For example, you can see fragments of objects in your visual field, and your brain searches for the best match to determine what objects you are seeing. This process is a complex enough addition that it deserves its own video. If we ignore for a moment Fido and dogs and collars, what the system is doing is encountering input patterns and remembering some. It doesn't matter what the inputs represent. This system doesn't interpret or decide what to remember, it simply remembers everything. This is another topic we'll address in future videos. This process of learning and recalling input patterns is completely different from learning as the word has come to be used in the AI field. That's not just a coincidence. AI learning is typically a math-heavy statistical process which has very little to do with how humans learn as well. Beyond the factual information I've shown in these demos, this type of graph can also learn processes, build mental models, and even learn algorithms. So there is no end of additional capabilities we'll want to add. That's where BrainSimulator 3 will come into play. It's a level up from Neurons, and it's a lot easier to add more complex functionality. In this final demonstration, I'll show the details of how this simulation works. I've set up just 2 cortical columns and 2 possible inputs and outputs, and the 6 fundamental relationship types. This example is small enough that we'll be able to zoom in on individual synapses. Inputs and outputs are clustered here for simplicity, but if you think of them as representing words, the input neuron fires if you hear the word, and the output fires to speak the word. In this demo, I'm just having 2 inputs, Fido and dog. The system uses 6 common relationship types. ISA and its inverse has instance, like Fido is a dog, and a dog has instance of Fido. Has a and its inverse part of, like a dog has a nose, and a nose is part of a dog. And finally, 2 more abstract relationships borrowed from computer science. This, which transfers input to output, and recursion, which transfers output back to input. If I fire one of the relationship types, you can see the gating signals flowing down to specific neurons in each cortical column. Starting again with an empty structure, when I first fire the Fido neuron, it allocates a column and connects to it. The neuron I've labeled request is the one which fires off the allocation process, which I've detailed in previous videos. The key element is that suppressive gate synapse coming from the input fired neuron, which fires if any input fires within any cortical column. If it does not fire, this is the trigger that a new column is needed. This is an example of many actions in the brain where the suppressive signal is the significant one. So if I fire the Fido neuron again, infired will fire because the connections has already been strengthened, and the allocation of the new column will be suppressed. These strengthened synapses have changed from blue to white, and there are 3 of them in each input row. Let's look a little closer. Now that we have a connection between Fido and column 0, we can see that firing the Fido neuron causes the in0 neuron to fire in the column. Similarly, firing the Fido star neuron causes the in0 star neuron to fire. And lastly, firing the out0 neuron in the column causes the Fido out neuron to fire. Why 3 neurons? 1 is input, another is telling the cortical column the desired output, and the third is the actual output coming from the cortical column. I don't see a way to avoid this apparent duplication because the signals are actually flowing in different directions and carrying different information. I've put the inputs and outputs together in a row because it's easy to explain. In your brain, though, the ability to recognize the word Fido is in a different area from that needed to say the word Fido. So there is no reason to assume that related inputs and outputs are anywhere near each other in the brain. The two neurons in between the Fido and Fido star neurons are needed for timing, and the last two neurons in the row perform inversion. That is, if I set the Fido neuron firing to fire a burst, then fire the inverse neuron, the Fido neuron will stop firing and Fido star will start. Fire inverse again and Fido star will stop and Fido will begin. It amazed me that this seemingly complex process can occur with just two neurons. Notice that signals arrive and leave the cortical columns in specific layers. This mirrors what has been observed in the layers of the neocortex. Well, that takes care of connections in and out of the cortical columns. Now let's walk through adding a relationship. And let's use my favorite, Fido is a dog. The key is in the relationship types. You can see the 6 relationship types, which are connected one each to specific layers in each column. That means that if I fire a burst on the Fido column, whenever a type neuron fires, a specific neuron in that column will fire as well. Each of these relationship neurons is connected to all column outputs with connection weights near 0. So all we have to do is fire the correct output and the connection will strengthen. So if we fire Fido, Isa, and Dog Star, the synapse will strengthen, like this. Once the synapse is strengthened, I can input just Fido and Isa, and the dog output neuron will fire. Now I'll remove that relationship by the simple expedient of manually setting the synapse weight back to 0.2. As a finale, I have a neuron over here labeled Fido is a dog, which conveniently fires the 3 neurons Fido, Isa, and Dog Star. Then, after a delay, it fires the inverse neuron. A single spike from the inverse neuron swaps the firing neuron so that dog, instance of, and Fido star are firing, which automatically adds the inverse relationship. This shows that with a few connections, whenever I add a relationship, the network could automatically add the inverse relationship. We can see the relationship we've just added by firing Fido and Isa, and then we could fire its inverse, dog and instance of. No artificial neural network I'm aware of has this capability of creating inverse relationships. These demonstrations prove the possibility of a neural system that can store and retrieve knowledge, handle attribute inheritance, and operate in a way that mirrors some of the efficiency of biological brains. And we're just scratching the surface of what this kind of architecture could achieve. Other key takeaways: when you give the system a pattern, it can store that pattern quickly and efficiently. Retrieval is fast, energy efficient, and scales well without exponential slowdowns. It's built on a neurally plausible model, and because the same structure repeats, you can scale it up, just like DNA builds your complete neocortex from a much smaller set of instructions. In future videos, we'll explore exactly how this graph structure can evolve, how concepts are selected, and how forgetting, reinforcement, and reasoning all emerge from a biologically inspired architecture. This will lead up to a complete model of how your brain works. If these ideas resonate with you, if you want to see where they lead, please like, subscribe, and hit the notification bell, because the YouTube algorithm won't surface videos like this unless you ask for them. And if you want to dig deeper, join the Future AI Society. It's free and help us shape the next generation of intelligent systems, and you can participate in our online conversations. And as always, thanks for watching.